In this video, I want to talk to you a little bit about power functions. Okay, something of the form f of x equals k times x to the a. Okay, that would be a typical way you might see a power function. Okay, so what do we know? We know that k and a are non-zero constants. Okay, k and a are non-zero constants. The a part is your exponent, or in this case, your power. Okay, that's the idea, power function. Okay, and k is going to be known as the constant of variation, or constant variation. Okay, so from some previous work you may have done, you might also think of these. I had an example ready for it, so I'll try and fit it here. You may have something as direct variation, and that would be like as one quantity goes up, the other quantity goes up. The more you eat out, the more money it's going to cost you. All right, so something like y equals k times x to the n. Okay, as x goes up, y goes up. Okay, the other type of variation, and I'll come back over here to make this fit in here, is known as inverse variation. All right, so inverse variation, y equals k over x to the n. Okay, or you may see it written as k times x to the negative n if we bring up that denominator. Okay, this one would be something like maybe the faster you drive your car, the less gas you're going to have. So as one thing goes up, the y value goes down. Okay. All right, so let's consider this example. The circumference of a circle varies directly as its radius, right? As either a direct or an inverse variation, or in other words, a power function. Okay, so the circumference varies directly as its radius. Okay, so what do you know? Circumference is equal to 2 pi r from back in your geometry days. So this 2 pi part is what we would call the k, which we talked about up here, is the constant variation, okay, for that example. All right, try this one. The force of gravity acting on an object is inversely proportional to the square of the distance from the center of the earth. Okay, so the force, I'll call it F, is inversely proportional. Okay, so inversely is like inverse variation. So you'll have a constant over the square of the distance. So I'll put down there d squared. So that would be an inversely proportional. Okay, next up, I put up here the word monomial. Okay, maybe you remember monomials back from Algebra 1. All right, so you can see that show up two ways. F of x could equal k, just a plain old constant, f of x equals 5. Okay, or maybe you have f of x equals k times x to the n. Okay, now a little restriction here. For these, k is still your constant. Okay, and then n has to be a positive integer. Okay, positive integer for your exponent on there. Right, so what do I mean? Just think about that for a second. If it's a positive integer, when you look at it, I'm saying no fractions. It's just another way to say it, okay? Another way to say it. No fractions, and there's no negatives. Okay, so it can't be negative, and it can't have fractions. And maybe one last thing kind of along those lines. Make a little bit of space here. Okay, so as we're kind of coming around here, if you have an f of x equals x to the n, and you find out that, or you observe that n is even, okay? That's going to tell you right away you have an even function. We've been talking about evens and odds, and I don't know that we've ever really summarized that, but if your exponent's even, you have an even function. If f of x equals x to the n, and your n is odd, I bet you know, you are going to have an odd function, okay? Maybe that seems kind of common sense, but I'm not real sure that we've ever put that down and made a statement like that, okay? So if your exponent even, you got an even function. Odd, odd function, okay? All right, one last thing here. I want you to be able to analyze functions, power functions, okay? So I have a couple written up here. Sorry to take a second to erase, but let's suppose I give you an example and I want you to analyze the power function. Power function. Oh, I don't know, maybe something like f of x equals the cube root of x. Okay, just to do something different. We do x squareds and so forth all the time, but maybe we could go through this. So think of this one as x to the 1/3 power, okay? So maybe the first thing I would ask you is, all right, what is the power and what is the constant? Okay, well, if you think back to right before I erased right here, you'll remember the power is up here as your exponent, so 1/3, okay? And your constant in this case, what's understood or implied here in front of the variable, you have a 1 there, okay? So you've got your power and your constant. If you were to take a peek at a graph, okay, something like that is what you would see if you put that in your grapher and take a look. So then we can go through and do our analysis. So we can start with domain, and remember, domain is still your x's, okay? So it looks like from negative infinity to positive infinity, okay? Range, talking about y's, looks like we're covered again, negative infinity, positive infinity, okay? I would next ask you, is it continuous? Is it a continuous function? And you're nodding your head, watching the video, yes, it's going to be continuous. Is it have anywhere where it is increasing? We have an interval of increasing. Well, it looks to me like the whole entire thing. So from negative infinity to positive infinity, we're increasing. So that means there's no decreasing. So I'm not even going to ask you. Do we have some symmetry? Symmetry? Well, I think this one, if you had this on your paper and you were to spin that around, you're going to see that we have symmetry about the origin, okay? So if it has symmetry about the origin, maybe we'll toss in also that it will be an odd function. Remember, origin, odd, those two go together, okay? How about min-max or extrema? Okay, extrema, on this one, no, we don't have any. Okay, in behavior. In behavior. All right, so when we describe in behavior, again, we're going to work with limit statements. Okay, so I want to know what's going on as x goes to infinity and also negative infinity. Okay, those are the two ends of your graph. All right, so let's do the negative one first. So we'll go from left to right. So as x goes to negative infinity, where's our graph going? If you have it on your graph, you'll see it's coming lower and lower and lower. So we're going to say that's going to negative infinity. The limit as x goes to positive infinity. So as we're going out to the right this way, our graph is getting higher and higher and higher. So it's going to positive infinity. What else do we have there? Oh, would this be an example of indirect or inverse or direct variation? And I said this would be an example of direct variation. Okay? All right, so there's a little problem where we go through and do an analyze. okay? So you'll be asked to do a little bit of that during this section, okay? Double check my notes. You know, I think I forgot to write this down at the very beginning. So this is a smidge out of order for your notes, but it'll work. 5 basic power functions. For examples, I got so excited to get my other examples, I skipped right over this. All right, the most simple power function. How about x to the first, or just plain old x? All right, so then think about this. You got x squared, x to the third. We could do x to the -1, which is your inverse function 1 over x, okay? Or x to the 1/2, which you may all recognize as the square root of x, okay? So again, these are your 5 basic power functions, and then we tend to kind of work off of those. All right, I hope this video has been helpful for you, and enjoy your power functions. Thank you.